In this section, we'll discuss strategies for designing for impact protection. Everything we discuss in this section will apply the principles of impact mechanics that we discussed in the mechanics of impact section, so be sure to have completed that section first. We'll focus on a few basic principles that underlie most impact protective solutions. The first is to use materials strategically to absorb forces that are applied to the body. The second is to decrease the velocity of the impacting object over a longer time. As we know from the impact mechanics section, this will reduce the acceleration component of the force, which reduces the amount of force that's applied. The third principle is to spread force over a larger area. In the impact mechanics section, we discussed how spreading force over a larger area reduces the amount of pressure that the body experiences. The fourth principle is to redirect force to less sensitive body areas, and the last principle is to consider the interaction between impact protection and other user needs like mobility and thermal balance. Let's start with absorbing force. The ability of a material to absorb force is closely related to its chemistry, the strength and resilience of the electrostatic forces and bonds between atoms and molecules within the material. When force is applied to a material, do those bonds bend? Do they break? Do they deform and then bounce back? Do they reorganize to form bonds with other molecules? All materials have what's called an elastic modulus, which is the amount of force that it takes to deform the material, which means to stretch it or bend it. Beyond that, each material has an elastic limit, the maximum amount of force that the material can take before it breaks. Very strong materials like Kevlar have a very high elastic limit, and weak materials like cotton have a low elastic limit. In some materials, the elastic modulus and the elastic limit are really close to each other. It only takes a tiny bit more force to break the material than it does to stretch it. For example, think about tearing paper. In other materials, the elastic modulus is way below the elastic limit. Think about a rubber band. It doesn't take much force to stretch a rubber band, but it takes a lot more to actually break it. What happens to a material after it's deformed is also of interest to us. Some materials stay deformed, like linen fibers for instance, and some bounce back, like polyester fibers. Materials that bounce back can return the force of the deformation. In a wearable system, they return that force to the body. For example, the soles of athletic shoes are engineered to deform and then recover, returning the force of the impact to the body to help propel the runner forward. This kind of collision is called an elastic collision, where the energy of the collision is preserved and then returned to the body. In the case of athletic shoes, where the body is trying to bounce off the ground, an elastic collision can be a good thing. But imagine a case like a car crash. You don't want the car to continue exerting the force of the collision on your body. You want to lessen that force and absorb it. Some materials are not strong but are elastic. For instance, open cell foam, the kind of foam that's in kitchen sponges, is easy to deform but bounces back after the force is removed. Open cell foams have holes that are all interconnected so that when you squish the material, air flows from one cell to another until it reaches the edge. A material can only return as much force as it absorbs, so a weak elastic material like a sponge can absorb only a little bit of force before it's flattened, and therefore can return only a little bit of force, which is usually not perceptible, but it allows the material to be used over and over again. Closed cell foams like neoprene are more like bubble wrap. They enclose gases in little bubbles that are suspended in the material. Because each cell is a closed bubble, when the foam is squished, the bubble deforms, but it can't flatten. That allows open cell foams to resist being flattened completely. Some open cell foams are more elastic than others. In neoprene, it's very hard to burst those bubbles. Lots of different materials can be foamed. For example, a kitchen sponge is an open-celled foam, but so is rigid insulation foam. The difference is the material that's being foamed, not the cell structure. The properties of the material dictate the properties of the foam. Kitchen sponges flatten easily but bounce back, while rigid insulation foam dents and doesn't recover. Materials that deform absorb force as they deform. It takes energy to reconfigure those bonds. In the 1950s, Mercedes-Benz patented a new approach to car design that challenged the idea that was more common at the time, that a stronger car body was better in a collision. Instead of engineering the body to withstand the most force possible, they designed a car that was engineered to collapse in a collision. Some of the force of the collision was absorbed by deforming all that metal, and in the process, the car's velocity was slowed over a longer period of time, reducing the acceleration of the impact and therefore the force that reached the passengers. Another way materials can absorb force is by breaking. Bending or deforming happens when the force exceeds the material's elastic modulus, but breaking happens when the force exceeds the material's elastic limit. Breaking or shattering a material can be a good way to both absorb force and distribute it over a larger area. However, if the collision force doesn't exceed the material's elastic modulus or elastic limit, the material will transmit the force to the body. In some cases, it will still spread the force over a larger area. Imagine if that plastic shin guard got struck by a ball. The force might not be enough to deform the plastic or break it, so the force is transmitted through the material to the body. However, because the material is stiff, the force is still spread over a larger area through the structure of the plastic and is experienced as smaller pressure on the skin. Materials that are very strong but flexible, like Kevlar fibers, are not able to distribute force to larger areas. A ballistic protection vest that uses Kevlar textiles is usually made of many layers of Kevlar, so that each successive layer slows the bullet or projectile down a little bit more until it doesn't have enough force to break the fibers. Kevlar fibers are very strong. It takes a lot of force to exceed their elastic limit. However, because they're not stiff, the force is still transmitted to the body and it's not spread over a large area, so the pressure that the body experiences is still high. To avoid the effects of pressure in very strong textile materials like Kevlar, stiff materials that shatter can help. Most ballistic vests use a combination of Kevlar layers and a ceramic plate. When a bullet strikes the vest, the plate shatters, absorbing force as it breaks and distributing force through the stiff ceramic structure. The shards and pieces of ceramic are contained by the strong Kevlar, and a new plate can be inserted to replace the broken one. Both bending and breaking are typically not reversible, so the protective material is destroyed after the collision. Some approaches try to limit this effect by partitioning the material into smaller segments so that the portion that's destroyed is localized. Dragon skin ballistic protection armor uses this approach. Instead of one ceramic plate, it uses smaller overlapping plates. The plate beneath the projectile will shatter and it'll transmit the force to the plates that it's touching, but because they're separate structures, those plates are less likely to also shatter. So the vest retains a better overall ability to protect the body, even when one part of it has been damaged. Stiffness can also allow forces to be relocated to less sensitive body areas. For example, in an athletic cup or breast protector, force that may be applied to the body in a sensitive region is redistributed to a less sensitive region through the stiffness of the material. Another way to slow velocity more gradually is to use fluid movement of liquids or gases. For example, think of the airbag in a car. When the car hits an obstacle, your body continues forward. The purpose of the airbag is to change your acceleration over a longer time by slowing you down. But remember that the airbag is inflating in the opposite direction to the direction you're moving, which would mean that you'd experience even more force if the airbag were a solid surface. In order to slow you down, the airbag is engineered to deflate as it's compressed. By squeezing the air out of it, you continue to move forward, but more slowly than you would have, since the bag applies a counterforce to your body. One of the most difficult aspects of protecting from impact is balancing the other user needs that are also critical to a good solution. Mobility is one of those needs. What good is it to protect an athlete from injury if the protection means that they can no longer play the sport very well? There are several methods that designers use to make thick or stiff protective materials more mobile. The first is segmentation. By dividing a material into sections, it can be made to flex along the division lines. Deciding where to place these divisions is important. In some cases, you might want stiffness or rigidity in one direction, or you might be placing the material over a bony segment that's already rigid in that direction. In other cases, you may want to make the material flexible in as many directions as possible. Superfabric is a cut-resistant fabric that's made here in Minnesota. It's made by printing dots of epoxy on a strong fabric base. This creates tiny plates that are laid out in patterns that are designed to keep a knife from cutting the base fabric, but still allow the fabric to move. Another approach is to layer the protective material so that flexible or stretchable gaps can be integrated into each layer. But because they align differently in the garment, the system provides protection everywhere. In historic armor, sliding plates were used to create articulated joints that allowed the joint to expand and contract, but still distribute force over a larger area through the rigid metal. Chainmail was used to provide stab and cut protection while still remaining flexible. Because chainmail drapes and conforms easily, it allows a lot of mobility, but it doesn't protect well from compressive impacts that happen over larger areas. In American football gear, a combination of sliding pieces and cantilevering is used to protect the shoulder. A cantilevered piece projects outward from the body, like the shoulder pad. When it's compressed, it deflects inward but also absorbs force through its structure. Thermal balance is another big variable in impact protection. Just like for mobility, adding more protection often compromises thermal balance. Many of the same approaches we discussed in the thermal unit can be employed here. However, with stiff and bulky materials, sometimes airflow can be difficult to achieve. Spacer materials can help, but another approach is to perforate the protective garment or system so that air can pass through. This must be done carefully so that the integrity of the material isn't compromised. Finally, more advanced material approaches can sometimes bridge these trade-offs more effectively. Shear thickening materials are fluid under low forces and solid under higher forces. They essentially stiffen on impact, which allows the material to be soft and supple when the wearer isn't moving fast, but become rigid when the material is struck by a projectile. They use the same principle as oobleck, that mixture of cornstarch and water that you may have played with at some point in school. Silly putty is another example. If you pull it slowly, it stretches, but if you pull it fast, it breaks cleanly. Shear thickening coatings are used on materials that need to protect from strong accelerations, but need to stay flexible during normal accelerations like body movements. They're used in body armor to improve flexibility and wearability while still offering puncture protection.